You may have noticed how we've seemed to define a rotational equivalent to all of the kinematics variables, and that was no accident. Because calculus doesn't care what symbols are used, only how they're related to each other, we can simply extend the linear results we had to rotational cases. So notice the parallels we have here. That for position, we have x in the linear case, and we called it theta in the rotational case. For velocity, we had v, but now we're calling it omega. And for acceleration, we had a, now we're calling it alpha. You can kind of think of that Roman letters are straight and Greek letters are rotations. That breaks down a little later, though. It's mostly true, but breaks down a little later. But the key thing is that because calculus doesn't care about what symbols are used, we can take all the equations that have these and just map over their equivalents to get true equations in rotational stuff. That is to say, we can take things like our x equals x0 plus v0t plus a half at square and just translate it and say, well, every x becomes a theta, every v becomes an omega, every a becomes an alpha. There's no such thing as rotational time, so it just becomes t. And so it must also be true that we can relate the displacement, the angular positions, via this equation. And likewise for the other two big equations that we used. This really comes from just making the same definitions and applying the same calculus to them. That allows us to solve problems that are analogous to the one-dimensional kinematic problems. For example, consider a disk starting at rest. If an axle provides a constant acceleration of 1.2 radians per second squared, how many seconds does it take for the disk to reach a speed of 350 radians per second? So here is our disk starting at rest. So omega 0 equals 0. We've applied an acceleration so that sometime later it's got a speed, we'll say it's going this way, and it's 350 rads per sec. And that's because we've applied an acceleration to the disk like this, which they tell us is 1.2 radians per second square. All right, we have initial and final speeds, and we have an acceleration, but we lack any distance, in this case an angle really, so we want to avoid theta in our equations. The best ones to use would be, of course, the omega equals omega naught plus alpha t, and solving that for t gives us 291.667 seconds, which for sig fig should get rounded down to 290 seconds. All right, using our usual thing of just solve this equation over for t, plug in, solve. Pretty straightforward. Another example, a wheel is rotating at 35 radians per second when a constant deceleration of 0.75 radians per second squared, as applied, I guess. How many turns, including fractions, will the wheel go through before it stops? Here we have an initial omega, which is going like this. And it's 35 radians per second. I suppose, to be honest, we might as well go the other way and say, well, they gave us a positive, so let's assume that it's spinning that way at 35 radians per second. Doesn't really matter, they didn't say. But then there is a counter acceleration, so going like that. That's pretty terrible. Sorry. Let's try that again. Thing which goes like this. And so that would be minus, or well, I guess alpha there would be 0.75 radians per second, but we'll enter negative in our equations. And then we end up with omega equals 0. In other words, it's at rest. And I guess we should say something like, let's assume it starts with theta equals 0, and that has gone around and is at some new theta final. Something like that. Here we have velocities and acceleration, and we're concerned with the angular displacement, because we don't know how much angle it goes through. What we don't have and aren't asked for is the time. So as usual, we avoid it in the equations using the omega squared equation to get us out. That omega squared is omega 0 squared plus 2 alpha delta theta. Then we can just do some relatively simple algebra. We say that we solve this over for delta theta, and we say delta theta is the difference in the squared velocities over 2 alpha. But we end at 0, and we start at 35, squaring them over here. And then on the bottom, we have 2 times a negative acceleration. Why? Because if it's moving at plus 35 but getting slower, it's got to be accelerating the other way. So we put in the 0.75 as a negative value. Grind all that out, you get 816.67 radians, which, looking at the sig fig, should probably be something like 817. But we're not done, and we're not correct, because we weren't asked for the angle. We asked how many turns it goes through, which is the number of revolutions. So we have to convert. And we might say that the number of turns divided by the angle has to be the same in the same ratio as 1 revolution divided by 2 pi radians. So then we put n over 817 radians equals 1 over 2 pi radians, and then cross multiply and solve, and we get 130 turns through which it goes. So interesting, these little Calvin Hobbes that I really enjoy, where the father comes along and he says, playing a record that is sort of a prehistoric CD. I'll show you something interesting. It's the compare point of the label on the point of the outer edge. So, and he says that they both make a complete circle in the same amount of time. So in the time it takes this to go around once, the outer edge, of course, also goes around once. So they're still aligned, and they're always aligned. And he says, but the point on the outer edge has to make a bigger circle in the same time, so it must be going faster. 2 points on one disk move at different speeds, even though they both have the same revolutions per minute. This gives Calvin some palpitations, as you can see, and it'll probably give you some from time to time, but it is true. The previous relationships that we came up with were analogies. The angular kinematic functions behave like their linear counterparts. But there are also direct relationships. The angular quantities are also connected to the linear ones. So we've got to be really careful here. There's 2 different ways that we're going to be talking here. On one level, theta is related to x because they play the same roles. They have the same calculus relationships. And v is related to omega because they play the same role. Their changes in position per unit time, and they have all the same relationships. But there'll also be a connection between, say, v and omega, or r, or between theta and x, and so on. All right, consider a bug on the edge of a wheel of radius r rotating at constant rate at period t. If the bug were to let go, it would fly off tangentially at some speed v. But there must be a connection between v and omega, because v is the distance traveled in time, and as it goes around the circle once, it travels the distance 2 pi r, and it takes time capital T. Because remember that capital T is defined as the time it takes to make one exact circuit. We can pull out the r, and we get 2 pi over capital T, but 2 pi over capital T was omega, so we get that v equals omega r. And that equation is going to come back. You're going to be using it over and over again. You're going to get used to it, hopefully. V equals r omega. Get used to where it comes from. This is saying the linear speed of something on the edge of a circle of radius r is related to its angular speed by just the radius. To be honest, we probably could have seen that anyway if you remember that our definitions were that the arc length is the radius times theta. The theta is defined so this is true. And if you're moving in a circle, of course, r is constant. So if I take time derivatives and I say take d dt out here, then of course by first law of algebra I have to take d dt in here. When I take the time derivative, it's a constant times something, so the constant comes outside. And we have something like that, which I suppose I could write a little bit cleaner that way. And over here we now have, remember, ds dt. But ds dt is the velocity, and d theta dt is omega, and everybody else has come along for the ride. And we get it again. That probably instantly tells you, well, what if I took another time derivative? What if I said d dt on this side and d dt on that side? And the same rigmarole would happen, of course, and we'd end up with that dv dt would be the acceleration, and this would, of course, be r d omega dt, which would be alpha, and we get the same connection. But here we need to be a little careful, because which acceleration is this? Well, this is the acceleration in the direction that the velocity was already pointing, so this is the tangential acceleration. And we'll talk about that again in a little bit, but we have to be careful here. All right, because we know that if you go around a circle, there's another important acceleration. Because this bug is traveling in a circle, we know it must have a component of acceleration towards the center, i.e. the centripetal acceleration, and it has to have magnitude of a sub c equals v squared over r. But we just found that v is omega r, and so we're able to take this and replace it with this, and then square both of them to get r squared omega squared, but there was an r on the bottom, so in the end we get that the centripetal acceleration is omega squared r. A different way of writing it. It's not new or spectacular, it's just a different way of writing it. It's particularly useful if for some reason you know omega, or that you know that it's constant. Right? For instance, if you have a solid disk, then they'll all share the same omega because the disk goes around at one speed, and so you can say the centripetal acceleration grows with the radius. All right, keep in mind always that how something changes compared to something else depends on what else is happening in the problem. If the v is held constant, then the acceleration goes down with the distance. But if omega is held constant, then the acceleration goes up with distance. And then here we see the other thing, sort of if the wheel is speeding up, then the bug has a component of acceleration along its line of motion, which we call tangential. And again, we get over here that tangential acceleration is r alpha. Tangential acceleration is indicative of changing speed, whereas centripetal acceleration is indicative of changing direction. So, a block is placed on a rotating disk and moves in a circular path. The disks in each of these problems have the same rotation rate, but the mass of the block and the distance to the center are varied. Draw a blue circle around the case with the greatest centripetal acceleration, and a red circle around the case with the least. And again, as we said, since omega is the same for all of them, we should probably use the one that says the centripetal acceleration is omega squared r. And in that case, we can just say it's just proportional to r, so we get that where r is largest, we get the most, and where r is least, we get the least. And then case B is just intermediate.